Hello, everyone, and welcome back to your channel of Math Made Easy in this series of trigonometry. So, I hope now you're confident and familiar with finding sine, cosine, tangent, or any other trigonometric function of any angle, really, whether it's positive or negative between 0 and 360 or beyond, if it's given to you in degrees or in radians. Today, before we proceed to some identities that you might have heard of, um, I want to go over two important laws that help us figure out, the dimensions of any triangle. Remember, trig meaning triangle, metry meaning the measurement. So this science is about how to measure the details of a triangle, like sides and angles and stuff like that, because that helps us a lot in real life. You must have, or even if you haven't heard, but you can see some easy problems that, for example, you are at one point, you have an instrument that will give you angles, and you want to figure out how far another object is. Maybe it's across a river, and you want to measure the distance from where you are to there, and stuff like that, or how high a building is. Okay, so we do that with the knowledge of, or the subject of learning how to measure a triangle. So two important laws that help us figure out that. The first one is called the law of sines. And this law says that if you have any triangle, acute, obtuse, right, scalene, anything. Okay, so let's draw any triangle. And you must have, if you figure, or if you watched some of the lectures or the sessions in the statics uh, sessions, you must have seen that. So I have a triangle ABC, and I'm going to refer to the opposite sides of every vertex with the lowercase letter. So if this angle is angle A, the side opposite to it would be lowercase a. If this is B, then this is lowercase b. And if this is C, angle C, this is lowercase c. What we say here is the following, that if I divide the sine of any angle, sine of A, I'm sorry, sine of A over the opposing length of the length of the opposing side, I get a constant, which is sine of B over B, or the sine of C over C. Not overseas, no. Okay. But what is this ratio? Do you know what this ratio is? Is the diameter of the circle that in which these three or this triangle is inscribed. So if I draw any circle, and within this circle I draw a triangle, I'm gonna draw a triangle here. So, and I'm going to make it such that one of the sides is the diameter, right? And I make any triangle. I don't care about these angles. I'm not here to prove that theorem. It can be proven, but that's not my point here. Okay, so we know that I can call the diameter, for example, A, B, or these are the angles, A, B, C, okay? And the opposite here would be A, B, C. So you know C is the diameter, right? And you should know also that the measurement of angle C is 90 degrees, right? Do you know that? You should have learned that in geometry, that if you draw a triangle in which where its hypotenuse is is the diameter, then the opposing angle is always going to be a right angle. So if the measurement of this angle is C, I know that sine C is 1. So what I'm saying here is sine C, or you can write it backwards. So you can say A over sine A equals B over sine B equals C over sine C. So here if I say C over sine C equals, well, sine C here is 1 since C is 90 degrees. So I get C over sine 90 equals C, of course. So it's not a proof, but it shows you that if this angle is 90 degrees in a triangle, then the opposing side is the diameter. So here I can say sine 90 over C equals the over C equals the diameter, which is C, meaning sine C is 1, right? So this law helps us a lot in figuring out a missing angle or a missing length if I know uh, some information about the other, or at least, some enough information to figure out that. Meaning, if I have these two, I know A and the opposing angle, and then you give me either an angle or a side, I can figure out the rest. Sometimes the law of sine by itself is not enough. Okay? I can find stuff, but I cannot find, for example, all the sides of a triangle. So here comes the law of cosine to the rescue. The law of cosines. And the law of cosines says that if you have a triangle, let's do the same thing. So I have a triangle here. Any triangle, it's not, an isosceles or equilateral. It just looked like that, but it's any triangle. A, A, angle B, angle C, and then side A, side B, side C. It says that if you know two sides and an angle, suppose I know A and B, and I know the angle between them. So you know two sides and the angle between them, like side, angle, side. Remember in geometry? So this is known, this is known, this is known. I can find the third side without further complications. I can say C square equals A square plus B square. And you say, wait a second, I've seen this before. This is the Pythagorean theorem, right? Yeah. If and only if this angle is 90 degrees. But if it's not 90 degrees, I subtract twice A times B. You say, wait a second, that looks like A minus B square. Yeah, but it's not, I'm not done yet. Times cosine of the angle C. Ah, so did you see here when if C is 90 degrees, cosine 90 is 0, so this term goes away, and you get the Pythagorean theorem. A square plus B square equals C square, if that was 90 degrees. Nice. And if I don't have a, if that collapses and becomes a line like that, okay? So the angle C here if it becomes zero, right, and the angle A becomes zero, and I want to calculate C square, I would say it's A square plus B square minus twice A times B times cosine 0, which is 1. So you get A minus B square. Do you see that? Because C square would be A minus B quantity square, because C here is 0, really. This value would be 0 because A in this case and B, A would be the same as B. So you say A square plus B square minus twice A times B, meaning minus twice A square, so you get 0. You don't have to worry about that. But what you should know is that if this angle is obtuse, you expect C square to be more than A square plus B square. If it's acute, you expect it to be less than A square plus B square. And if it's a right triangle, it's exactly A square plus B square. And that's why if this angle is obtuse, the cosine is negative, and negative times negative is positive. So you end up with a value greater than A squared plus B squared. Between these two, you can solve really anything. Meaning, let's take an example. Let's say I have a triangle. Let's draw any triangle. I don't care what. I don't know except the following. Let's say we measure that. So we get, let's say 7.5. And let's say this is, well, it doesn't matter. It's not like 9. Okay, whatever. It looks like 9. And then I tell you, um, let's see if you know what this angle is. Let's say 40 degrees. And let's call these A, B, C, A, B, C. Here, I can say the following. I know two sides and the angle between them, so I can find B by saying B square equals A square, which is 56 and a quarter, plus B square, which is 81, minus twice times 7.5 times 9 times cosine 40 degrees. Of course, you will not get an integer number. I think we already changed the mode. No, I returned back to radian because we were doing the radian last time. Okay. So let's say I'm going to take the square root, because notice that will give me B squared. So B equals the square root of 7.5 square plus 9 square minus 2 times 7.5 times 9 times cosine 40. So I get 5.8167. 5.82. Okay? And now I can say that 5.82 over sine 40 is the same as 7.5 over sine C, I'm sorry, A equals 9 over sine C. So to solve for sine A, I can say sine A equals 7.5 sine 40 degrees divided by 5.82. And sine C equals 9 times sine 40 over 5.82. Okay, so I'm going to do it one step at a time and then we'll see. So 9 sine 40 divided by this number will give me 0.9984. No, oh, I did this one first, right? And 7.5 sine 40 divided by this number gives me 0.8288. So how do I find the angle A and the angle C? Here, you get the inverse function. So you say it's the inverse sine. We call it arc sine, and we write it as ASIN for arc sine or inverse sine. Okay, we prefer to use arc sine. So arc sine of 0.8288, and this is arc sine of 0.9945. Okay, so I'm going to, you see, you do second sine, and you can see sine or the arc sine written here, right? Let me enlarge, oops, this, and make it larger so you can better see that. Okay, so if I do arc sine, here it is, this number, I get 84.02 degrees. And if I take arc sine of that number, I get 55.97 or 98 degrees. As a quick check, I'm going to say this angle plus that angle plus 40 degrees, because the third is 40, and check it to see if it's 180 or not. Sure enough, it's 180, so I did it correctly. And you can see that between the law of sines and the law of cosines, even if you don't have a right triangle and you don't know the sine or the cosine of these angles, you can easily find all the information about the triangle. So you can find the side length as well as the angles quite easily. And those, between these two laws, as I said, you can find anything you want in a triangle. Given, of course, enough information, because if I tell you A is 5, find the rest, and you say, how? I mean, if this is 5, I can have infinite number of triangles with one side of them being 5, right? If you give me these two, it's still not enough. But if you give me another angle, not necessarily. Well, if I can give you, for example, uh, two angles and a side, right? So if I give you these two angles and say side A, you would say, okay, if these two angles, I know these two, I can find the third by subtracting from 180. And once I have the three angles, I use the law of sines and I get that. If you have two sides and an angle between them, you can find also using the law of sines and cosines, everything else. Okay, so that was also an important topic I wanted to go over before we move next session to the identities in trig. Okay, thanks for your watching and hope to see you soon.